Hi guys, welcome back. We're finally going to have a look at some integration, which is the whole purpose of the chapter. Question 9, by the way, is where they start actually asking some integral questions. So I don't know if this is an appropriately named chapter. But anyway, we're just going to use some of those formulas from before. So just as a refresh, if we wanted to find the derivative of the inverse sine function, that's going to be equal to, that's going to be equal to 1 over the square root of a squared minus x squared. If we wanted to find the derivative of a cos function, that's going to be equal to negative 1 over the square root of a squared minus x squared. And if we wanted to find the derivative of the inverse of tan for x over a, that's going to be equal to a over a squared plus x squared. Okay, so let's go ahead now and let's use these functions. So if we're going to find the derivative of a function, this will be the solution. So what we're doing now is we're going from the solution and we're working backwards. So we're finding the antiderivative of this function here. And I hope that you can appreciate that this function is in this form here. If it was a negative, we would be using the cos function. Alright, so since this is in this form here, let's rewrite it in terms of a. So we could rewrite this as the integral of 1 over the square root of 10 squared minus x squared dx. And so now it's really easy to see that a is going to be equal to 10. And so to find that integral now, that's just going to be equal to the inverse of sine x over 10 plus c. Very simple. Let's do another example. A little bit more complicated, but not really, because all we're going to do with this too for our numerator is this is a scalar constant, so we can just pop that out the front of our integral. So we can rewrite that as 2 lots of the integral of 1 over the square root of 4. 4 we can rewrite as 2 squared minus x squared, and we're integrating with respect to x. And again, we can now see that this is exactly the same as the inverse sine function again. So that's going to be equal to 2 lots of the inverse sine function x over a, and a is equal to 2. So x over 2 plus c. I think we should do maybe one more of those slightly more complicated examples with the 2 or other number as a numerator instead of 1. All right, slightly more complicated example again, but again we can pop this scalar factor out the front so that we have 12 lots of our integral 1 over the square root of 64 minus 9x squared dx. Now with this, in previous examples with this formula, I'm assuming this is going to be the inverse sine function because when we found the derivative of the inverse sine function, that was the same as the value positive 1 over a squared minus x squared, not minus 9x squared. So what I'm actually going to do is I'm actually going to let u equal to 9x, and then when I rewrite this, I can rewrite this as 12 1 over the square root of 64 minus 3, because then this will be u squared in here. And I should also write that as 8 squared as well. Let me change that. Okay, there we go. Just fixed up those couple of little boo-boos. All right, the last thing we need to do is we need to deal with this dx situation. So what we will want to do is we will want to replace this with du, so then we can integrate with respect to u rather than integrating with respect to x. We can only ever integrate or differentiate with one variable at a time. So again, we can just do that by finding this derivative here. So the derivative of u with respect to x is going to be equal to 3. And so du over 3 is going to be equal to dx. And du over 3, remember, is the same as writing 1/3 du. So this is just another scalar factor that I can just pop out the front here. So let's rewrite that as 12 over 3, which we know is going to be 4, du. So now we can derive with respect to u instead of with respect to x. And this is in this form here. So this is just going to become 4, because 12 over 3 is 4, times by the inverse of sine x over 8 plus c. And that's it. So those are some simple familiar examples with increasing complexity, showing you how to find the integral of those functions. So jump in for the next video. The next video, excuse me, Belle, the next video is going to be some more complex familiar examples.